Welcome to the Consulting Specifying Engineer webcast, Critical Power Hospital Electrical Systems, sponsored by ASCO. I'm your moderator, Jack Smith, with the Consulting Specifying Engineer, Pure Power, and CFE Media. Here's a list of the learning objectives for today's webcast. We'll cover these in today's presentation. Now let's meet today's presenters, Dana Jensen and Robert Jones, Jr. Dana Jensen has more than 15 years of experience at CCRD, a WSP Parsons Brinkerhoff company in Dallas, where she became Associate Principal in 2012. Most of her work consists of designing electrical distribution for hospitals, and she also designs electrical systems for medical office buildings, data centers, and retail facilities. Her duties also include project management and quality control for major projects, which requires knowledge of mechanical, electrical, plumbing, and fire protection systems, as well as commissioning. Dana is a member of the Consulting Specifying Engineer Editorial Advisory Board. Robert Jones, Jr. is a Senior Project Engineer at JBA Consulting Engineers with more than 12 years of design experience. He has experience in various market sectors, including hospitality, commercial, medical, and government projects. He is involved in project design from schematic preparation through construction administration. Rob is a LEED certified and specializes in technical and complex designs, including but not limited to low and medium voltage distribution systems, emergency and standby power systems, renewable energy design and implementation, circuit analysis calculations, and equipment spacing planning. Thank you, Dana and Rob, for joining us today. And Dana, you're up first, so the floor is all yours.
Well, thank you, Jack. As he said, today we're going to discuss the intricacies of designing electrical hospital systems. First, we're going to cover the following topics. We're going to start with the applicable codes and standards. We'll review the definitions of healthcare facility types and where these codes are applicable. We will discuss the specific wiring requirements as well as the various patient care space requirements. Then we'll review the essential electrical system requirements. We will touch on transfer switches, and we'll discuss how these systems differ for hospitals versus other types of buildings. And we will leave you with a few case studies and some generator sizing tips. So hospital electrical systems are definitely complex and subject to a plethora of codes and standards. So we'll start with just the NFPA codes. First, you have NFPA 70, and within this code, there are several applicable articles dealing with healthcare facility design. Those include Article 517, which is really the meat of the requirements for healthcare facilities, but the engineer must also be familiar with the Chapter 700 articles, including 700, 701, 702, and sometimes even 708. Then you have NFPA 99, which is the Healthcare Facilities Code, and it focuses on all systems in healthcare design, including medical gas installations, HVAC requirements, and so on. Chapter 6 of this code is specific to electrical systems, which is what we will focus on today. And then you have NFPA 110, which is the standard for emergency and standby power systems. This code focuses at the source equipment and provides specific design, installation, and testing requirements of the main emergency power supply system. Once you digest the NFPA code requirements, there are additional standards that you must follow, including those adopted by state and local health departments. First off, you will have the FGI, or the Facilities Guideline Institute for Hospitals and Outpatient Facilities. While this is called a guideline, many jurisdictions consider this to be the enforceable code. However, there are several state-specific codes, such as California, Florida, Michigan, Texas, just to name a few. The FGI guidelines, or state-specific codes, depending on where you're at, include many of the same or similar requirements as NFPA 70 and 99. However, they are also much more specific on the code requirements within each department of a hospital. The guideline is specifically divided up into departments you would expect to find within a hospital, such as surgical suites, patient rooms, emergency departments, imaging suites, and so on. And each one has their own abundance of requirements, such as the quantity of receptacles, light switching requirements, nerve call requirements, the list goes on. And then there are a few other standards that out there that weren't mentioned, such as the ASHI handbook. This one includes numerous diagrams on distribution systems and tips for electrical safety, power quality, maintenance testing. This handbook mainly is just a handbook to be referenced by the designer for a more reliable system. I have not run into a jurisdiction yet that views this as code. Just be aware that it's out there. And once you think you have it all figured out, there are also operational standards that, depending on your hospital license, they must adhere to. These aren't construction codes, but you will hear facility directors speak of additional standards or requirements such as the Joint Commission or the Centers for Medicare and Medicaid Services that you must be aware of. So it can become a bit overwhelming when you realize how many codes and standards there are. And of course, they're all updated on a regular basis. However, it is the job of the electrical engineer to know these codes and how to apply them. As you would expect, with each of these applicable codes and standards, there are definitions within them. Both NFPA 70 and 99 define a healthcare facility as buildings or portions of buildings that include but are not limited to hospitals, nursing homes, limited care facilities, clinics, medical and dental offices, ambulatory care centers, and psychiatric hospitals. The other important definition to understand is healthcare occupancies. NFPA 101 defines this as an occupancy used to provide medical or other treatment or care simultaneously to 4 or more patients on an inpatient basis where such patients are most likely or mostly incapable of self-preservation, basically due to age, physical, or mental disability. So the term healthcare occupancy should not be confused with the term healthcare facility and how these codes are applicable. All healthcare occupancies are considered healthcare facilities. However, not all healthcare facilities are considered healthcare occupancies. For instance, a medical office building can be a medical facility, but under NFPA 101, it would typically be a business occupancy and not required to follow NFPA 99 or Chapter 517 of NFPA 70 for hospitals. The NEC and NFPA do not designate the type of facilities or level of care provided. The governing body of the facility determines that type of service. But once you are deemed a healthcare occupancy, you can be further classified as things like a nursing home or a hospital, which have their own regulations. For today, the hospital requirements that we plan to focus on are in Chapter 517 of NEC. And it defines a hospital as a building or a portion thereof used on a 24-hour basis for the medical, psychiatric, OB, or surgical care of 4 or more inpatients. So now that we've overloaded you with code information, Rob is going to go into some of the unique and specific electrical systems required in a hospital.
Thank you, Dana. Now let's take a look at some of the wiring method requirements in NEC 517 for healthcare facilities. NEC 517 Part 2 covers all of the special wiring and protection requirements in a patient care space. Some of the non-patient care spaces that are not covered by this section include business offices, corridors, waiting rooms, and similar areas in clinics, medical and dental offices, and outpatient facilities. These spaces would fall under NEC Chapters 1 through 4. Article 517 contains stricter wiring method requirements for patient care areas and not only ensures adequate and reliable power is available to treat a patient, but also help prevent shocks. Patients may be in direct contact with electromedical devices, and it is important to minimize voltage potential between conductive surfaces likely to become energized and conductive surfaces that may be in contact with the patient. So before we dive into the requirements, here are some important terms defined in NEC 517. A patient care space is a space within a healthcare facility wherein patients are intended to be examined. The patient bed location is a location of a patient sleeping bed or the bed or procedure table of a patient care area. Now, I should mention the 2014 edition of the NEC changed several definitions in Article 517. For example, the patient care area is now the patient care space. However, some instances of this change were missed in this code cycle, but were picked up in the 2017 edition. So I may have area and space intermixed in here if I didn't catch them all. The patient care vicinity is a space wherein a location intended for the examination and treatment of patients extending 6 feet beyond the normal location of the patient bed, chair, table, treadmill, or other device that supports the patient during examination and treatment and extending vertically 7 feet 6 inches above the floor. The patient care space is defined by 4 varying degrees of possible injury to the patient or caregiver as a result of an electrical system failure. A basic care space is a space in which failure of equipment or a system is not likely to cause injury to the patients or caregivers, but may cause patient discomfort. Some examples of basic care spaces are examination or treatment rooms in clinics and medical or dental offices. A general care space is a space in which failure of equipment or a system is likely to cause minor injury to patients or caregivers. Patient bedrooms, exam rooms, and treatment rooms where a patient may come in contact with electromedical devices are all examples of a general care space. Electromedical devices are medical equipment used for diagnostic or therapeutic treatment, such as imaging equipment, ultrasound, monitoring equipment, or electrocardiogram. A critical care space is a space in which failure of the equipment or system is likely to cause major injury or even death to patients or caregivers. Critical care spaces may include intensive care units, angiography labs, cath labs, delivery rooms, and operating rooms where patients are intended to be subjected to invasive procedures and connected to line-operated electromedical devices. And lastly, a support space is a space in which failure of equipment or a system is not likely to have physical impact on patients or caregivers. These spaces may be anesthesia workrooms, sterile supply labs, waiting rooms, etc. All wiring in patient care spaces that serve receptacles and fixed electrical equipment must have 2 ground paths. The first required pathway is via the metallic raceway system or a cable having a metallic armor or sheath. The raceway system or cable must be suitable as an equipment grounding conductor in accordance with NEC 250.118. The second required path is with an insulated equipment grounding conductor. The insulated equipment grounding conductor must be connected to the grounding terminal of all receptacles, metal boxes, enclosures containing receptacles, and all non-current carrying conductive surfaces of fixed equipment likely to become energized. HFC, or Healthcare Facility Type AC cable, qualifies since it has a copper or aluminum strip in contact with the armor, as well as an added insulated grounding conductor. Also, as shown on the right, HFC type MC cable also qualifies. This cable has the standard insulated copper equipment grounding conductor, but in addition, there is an uninsulated aluminum conductor in continuous contact with the outer sheath. The equipment grounding conductors are sized per NEC 250.122. There's normally 2 or more circuits that may serve a patient care vicinity. The panel boards that provide circuits to the same individual patient care vicinity must be bonded together with an insulated continuous copper conductor. The code says that the minimum conductor rating is number 10 AUG. Isolated ground type receptacles are not compatible with the grounding requirements in the patient care vicinity. Since the equipment grounding terminal is isolated from the metal mounting yoke, the raceway grounding path is not available to equipment supplied by the receptacle as the ground fault current path. In previous code cycles, isolated ground receptacles were prohibited entirely from healthcare facilities. The 2014 edition revised this, and NEC 517.16 precludes their use in the patient care vicinity. Use is permitted in other areas such as a nurse station. Hospital-grade receptacles are similar to general use receptacles, except they include increased grounding reliability, assembly integrity, strength, and durability. If you have ever used an old receptacle with fatigued contact tension, you would understand the concern when the equipment supplied by the receptacle may be supporting life support equipment. NEC 517.18b and 517.19b2 require hospital-grade receptacles at the patient bed location. Identification of critical branch supplied receptacles is very important to ensure medical equipment is connected to a reliable source. NEC 517-18A and 517-19A require the critical branch receptacles or the cover plate to be identifiable with a distinctive color marking, usually red, and also indicate the panel board and circuit number supplying them. The last special receptacle requirement I'm going to mention now is for pediatric wards. Receptacles installed in patient rooms, bathrooms, playrooms, and activity rooms in pediatric units must be listed tamper-resistant per NEC 517.18c. I want to quickly mention two distribution branches of the essential electrical system, the life safety branch and the critical branch. The life safety branch, similar to emergency systems under NEC 700, is for safe evacuation of the building in an emergency. The critical branch supports lighting and equipment for effective hospital operation. Dana will cover these in more detail shortly. NEC 517.30C1 requires the wiring for the life safety branch and critical branch to be kept entirely independent of all other wiring and equipment, including from each other. That means separate raceway systems, including conduit supports, boxes, etc. Mechanical protection from damage of essential electrical system, life safety, and critical branch wiring is addressed in NEC 517.30C3. If you recall in an earlier slide, the branch circuits in patient care spaces had a requirement for the raceway or cable system to be suitable as an equipment grounding conductor. This requirement precludes the use of any non-metallic raceways in patient care areas. Notwithstanding that, there are 5 wiring methods permitted. The first is non-flexible raceways, type MI cable, type RTRC-XW, or Schedule 80 PVC conduit. For those that may not know, RTRC-XW is fiberglass conduit. It's expensive. The second is where encased in at least 2 inches of concrete, Schedule 40 PVC, flexible non-metallic or jacketed metallic raceways, or jacketed metallic cable assemblies listed for installation in concrete. The next method is listed flexible metal raceways and listed metal sheath cable assemblies when used in listed prefabricated medical head walls, listed office furniture, in existing walls or ceilings not subject to physical damage, and flexible connection to equipment. The fourth method permits flexible power cords for appliances and other utilization equipment. And lastly, cables for Class 2 and Class 3 systems may be installed with or without conduit. Now we'll take a look at some of the special requirements in the general and critical care spaces. In a general care space, each patient bed location requires at least 2 branch circuits, one from the normal system and one from the critical branch. The normal branch circuit may alternatively be a critical branch circuit if that circuit is supplied from a separate transfer switch from the one supplying the other critical branch circuit. When more than one normal branch circuit is supplying an individual patient bed location, all normal circuits must originate from the same panel board. A minimum of 8 receptacles must be provided at the patient bed location. These 8 receptacles may be any combination of single, duplex, or quadruplex type. The branch circuit minimum quantity and source requirements in a critical care space is the same as a general care space. The quantity of required receptacles is stepped up to 14 receptacles. In addition, at least one of the critical branch receptacles must be on a critical branch circuit dedicated to the individual patient bed location. An operating room is a critical care space with additional requirements on top of other critical care spaces. There must be at least 36 receptacles in any combination of single, duplex, or quadruplex type. At least 12 of the 36 receptacles must be connected to either the normal branch circuits or critical branch circuits supplied from a separate ATS than the one supplying the remaining receptacles that are connected to the main critical branch circuits in the operating room. Another consideration is whether the operating room is going to be a wet procedure location. A wet procedure location is the area in a patient care space where a procedure is performed that is normally subject to wet conditions while patients are present, including standing fluids on the floor or drenching of the work area, where either such condition is intimate to the patient or staff. These locations may include areas such as hydrotherapy or dialysis labs and are generally at the discretion of the hospital governing body. Many hospital governing bodies consider an operating room to be a wet procedure location. NEC 517.20A requires additional special protection from electric shock in wet procedure patient care spaces. The first option is to install a power distribution system that limits the ground fault currents without interrupting the supply. An isolated power system will provide this type of protection. The second option is a system that interrupts the supply if the ground fault current exceeds 6 milliamps. This could be GFCI protection. In an operating room where invasive procedures occur, interruption of the power supply could have devastating consequences. Normally, an isolated power system is installed in these spaces. An isolated power system is an ungrounded distribution system with a monitor to alarm when leakage current from a ground fault occurs. The circuits remain energized during a line-to-ground fault, but also keep the patient from experiencing electric shock from the leakage current. NEC 517.160 contains provisions for isolated power system installations. The isolation transformer may only serve one operating room. There are a couple of exceptions for induction rooms that may serve more than one OR, and also equipment operating at higher voltages, above 150 volts. The circuit breaker serving the isolated branch circuits must disconnect all conductors simultaneously. This is an ungrounded system, so both conductors serving a single pole circuit must be opened. The conductors are also not permitted to be installed in a raceway system that contains conductors from other systems. In a typical single pole application, one conductor must be identified with orange and at least one distinctive colored strip other than white, green, or gray along the entire length. The other conductor must be identified with brown with the same requirements for the stripe. Lastly, the isolation monitor measures and displays the total hazard current along with alarm display lights. Now I'll hand it back to Donna to talk about the essential electrical system.
Well, thank you, Rob. So as you said, we are going to now focus a little further upstream in the electrical design with the source equipment and the main distribution equipment. This equipment is all lumped together and called the Essential Electrical System, or the EES. The EES as a whole is defined as a system capable of supplying lighting and power essential for life safety and orderly cessation of procedures during the time normal electrical service is interrupted. The EES is comprised of the alternate source, which is typically the generator, and all of the connected distribution systems, including automatic transfer switches, distribution and branch panel boards, as well as their associated feeders. NFPA divides the EES into 3 branches: the life safety, critical, and equipment. It provides details on the minimum quantity of ATSs required. However, any of these branches are permitted to be divided into sub-branches for added reliability or as required by the connected load design. Here is a very simplified diagram of an EES for a hospital. And if you are familiar with older versions of the code, you will notice a change in terminology here. Formerly, the critical and the life safety branches were grouped together and called the emergency system. This has been completely removed in the 2014 NEC, and now all 3 branches are referred to collectively as the EES. This was a change to both the 2014 NEC and the 2015 NFPA 99. In addition, there's new verbiage in these codes that state, for the purposes of this code, the life safety branch must comply with Article 700, which is emergency systems, in the NEC. This was added to clarify the relationship between Articles 517 and 700 of NFPA 70, so that it's intended to that only the life safety branch of the EES comply with Article 700, not the critical and equipment branches. So the life safety branch is the most clearly defined branch in NFPA. It lists exactly what is required to be connected to this branch and stipulates that this and only this is what may be connected. It includes the following: egress lighting, exit signs, alarms and alerting systems, which include fire alarms, medical gas alarms, and mechanical control alarms required for effective life safety system operation. This includes communication systems, both illumination and receptacles at generator set and transfer switch locations, and generator set accessories, including fuel pumps, ventilation fans, louvers, controls, cooling systems, basically anything that's going to keep that generator up and running. It includes elevator cab lighting, controls, and communication. Note, this is not the elevator motor itself. That belongs on a different branch. This is just the cab lighting, controls, and communication themselves. And finally, automatic doors used for building egress. The critical branch also lists items that are required to be on this branch. However, the code leaves this one a little more open to put items other than those that are just called out in the code, as long as they're required for effective hospital operation and not already listed as being required on a different branch. These items include all of the following: task illumination, receptacles, and fixed equipment in critical care areas, isolated power systems, so the systems that Rob was just talking about, illumination, receptacles, and fixed equipment in patient care areas, including the list you see here. I'm not going to read that to you. But then, of course, and if that was not enough, it then gives you that coverall of additional illumination and receptacles needed for effective hospital operation. So as I mentioned, this allows you to include other things that aren't necessarily listed here as new departments continue to emerge in hospitals or whatever. This doesn't preclude you from putting, imaging departments on emergency power because you have that caveat there. The equipment branch is the third branch, but this one is actually listed in two sections of the NEC. It's in Article 517.34, both Parts A and Parts B. Part A requires automatic connection, and Part B lists items that are permitted to actually be manually connected. So the following items are required to be automatically connected to the equipment branch: medical air and vacuum equipment, sump pumps, including their controls, compressed air systems serving medical and surgical functions, smoke control and stair pressurization systems, kitchen hood supply and exhaust systems, supply return exhaust systems for isolation rooms, labs, protective environment rooms, nuclear medicine areas or other areas where radioactive material is used, operating rooms, and anesthetizing evacuation equipment. And brand new for the 2014 NEC, it now also requires AC systems for data and telephone equipment rooms and closets. So this is important to note because it could affect that mechanical design. If the mechanical engineer is designing those rooms to be served just off of the VAV boxes, off of a regular old chilled water air handler unit, you better have a chiller on emergency power. Or you can instruct your friendly mechanical engineer to design a dedicated system for these rooms, such as a DX fan coil unit or something that's a little more manageable on the equipment branch system. A couple of exceptions do apply here. The medical air and vacuum systems are allowed to be on the critical branch, and a handful of other things. Basically any other systems that could potentially be hindered if connected to a delayed connection or on a shuttable branch. So just note there's exceptions there. And then Part B of the equipment branch is what is permitted to be manually connected. Again, nothing precludes you from connecting this stuff automatically. The code just allows it to be a manual connection as an acceptable means. This includes heating equipment serving operating rooms, labor and delivery rooms, critical care rooms, nurseries, which include NICUs, isolation rooms, emergency departments, and patient rooms. Note there are also some exceptions here depending on the climate you're in and what that ASHRAE design temperature is. Additional equipment includes pressure maintenance pumps such as jockey pumps for fire protection, elevator, at least one elevator that provides access to patient floors, surgery floors, OB, and the ground or exit discharge floor, hyperbaric and hypobaric facilities, automatic doors, autoclaving equipment or sterilizers, and controls for all the equipment listed here. And then again, just like the critical branch, there's nothing that limits you from putting additional equipment on this branch as long as it doesn't already belong on a different branch and is required for effective hospital operations. So this could be items such as chillers or additional air handler units or other things that you would want on emergency power. So now we've figured out what belongs on each branch. Let's discuss how you create those branches within the system. As you recall from the diagram that we showed earlier, the branches are created by the use of transfer switches. Typically, you'll have a minimum of one per branch, but there are exceptions if your system design is less than 150 kVA. The key here is to work through your design and provide the appropriate number of switches. The larger your system is, the more switches you may desire. It creates added reliability as well as helps to step load the generator by applying your loads one at a time. Another thing to consider is load shedding. Where you have a system with multiple generators, you need to plan for an emergency case scenario where you may lose one or more of your engines, but you still need to maintain your life support systems. In this situation, the life safety and the critical branches must remain functional. Therefore, you have to drop something, so the equipment switch would need to drop in order to avoid overloading the system. So here you can just see a sample ATS schedule from a project where you have more than one generator. So you want to make sure that you're identifying the priority levels of the switches and how they react upon the loss and restoration of power. And you can see here that your priority 1 branches are connected immediately to the bus once it senses power and are never shed. They are also the first to switch back once normal power is restored. And the equipment and optional branches are stepped on later to avoid overloading the system. So there are many additional transfer switch requirements listed in the codes, especially NFPA 110. So that's kind of a separate seminar all in itself. So here are just a few highlights that you should be aware of in the design and specification of your switches within the EES. First off, mechanical interlocking is required to prevent inadvertent connection of the primary power supply and the emergency power supply. Transfer switches must be electrically operated and mechanically held. They are required to be listed specifically for emergency use, and this listing must be by an independent third party, such as UL. They must supply only emergency loads, which are the loads we just discussed earlier for each branch, and they must be suitable for the operation of all functions they are intended to supply. For instance, if it's going to feed inductive loads or nonlinear loads, it must be designed and suitable for that use, such as the switch capacity or interrupting rating. As if all this wasn't enough, there are some additional requirements that you must be aware of in your system design. One is the requirement for the branches to be separated from other circuits. Now, Rob touched on this from a branch circuit level. The codes also talk about this at all the way up at the distribution level. The requirement lists that branches must include physical separation from each other. So this can be done two ways, either with vertical switchboard sections, which is the most common, or you can also do it via separate enclosures, such as a set of enclosed circuit breakers lined up near the generator. And in addition, NFPA 110 requires your EES equipment to be in a separate room from your normal power service equipment. Again, exceptions here apply for smaller services. But it's very important to understand at the beginning of a project when laying out your electrical rooms, because as you can see from the photo here, the equipment can start to get very large once you adhere to all the requirements, and this is just the emergency power room. And another requirement is selective coordination. A brief overview of what is meant by selective coordination is where a system is designed to help isolate a fault and not affect unnecessary equipment. So here, the diagram to the right shows a system lacking selective coordination, so there's a fault way downstream and everything highlighted in red has tripped. So the system on the left is a system that has been properly coordinated and isolates the fault as close to the condition as possible, leaving the rest of the system up and running. Now, something that was added in 2014 version of NFPA 70, Chapter 517, now limits selective coordination requirements for a fault duration of 0.1 seconds and beyond. This differs from the requirements of Article 700, which requires full selective coordination, which is typically interpreted to mean 0.01 seconds and beyond. NFPA 99 relaxed this requirement in the 2012 version, and now we got caught up with it in NEC in 2014. But this is real good news for the healthcare world because it allows the engineer to really consider the other factors, such as arc flash hazards, equipment damage, risk of fires, or extended outage concerns, which are harder to accommodate when designing to meet Article 700. So now back over to you, Rob.
Thanks, Dana. So the essential electrical system for hospitals in a way loosely parallels the emergency and legally required standby systems used in other buildings. NEC 517.26 indicates that the life safety branch of the essential electrical system shall meet the requirements of Article 700, except as amended by Article 517. NEC Article 517 takes things a step further and contains more prescriptive requirements, including detailed lists of loads, as Dana mentioned, that may be connected to each system, as well as stricter wiring methods. Next, we'll take a look at some of the differences between NEC 517 and 700. Here we see a list of acceptable sources of power for a hospital. In a hospital, there must be two sources of power for the essential electrical system. The normal supply is typically the utility, but could also be an on-site generating plant. The alternate source may be either a generator or a battery system. The source must be located on-site. If the normal supply is an on-site generating plant, then the alternate source may be an external utility service. You'd have to check with the hospital governing body or the local AHJ to confirm that, though. Emergency systems and other building types have a few more options. Again, the normal supply may be the local utility. The alternate supply may be a generator, a battery system, a UPS, a fuel cell system, or unit equipment, such as battery packs and lights. Where approved by the local HJ, a second utility service that is completely separate from the normal supply may be permitted. Another difference is how the generator rating is determined. NEC 700 and 701 require the generator to have enough capacity to run all of the connected loads at the same time. The generator is permitted to support emergency, legally required standby, and optional standby systems. If the system design includes selective load pickup and shedding to ensure the emergency and legally required loads are fully supported, capacity reserved for the optional standby system may be demanded. NEC 517 permits practical sizing of the generator capacity using prudent demand factors and historical data, in addition to the connected loads and Article 220 calculations. Since the essential electrical system can often have a multitude of non-coincidental loads, it is not unheard of an actual demand on the generator of less than 30% of the connected loads. When a diesel generator is operating below 30% capacity, the engine cylinders and exhaust system may experience wet stacking. This is caused by an incomplete fuel burn and over an extended period of time can seriously degrade engine performance. Allowing a designer to size the generator closer to the expected peak demand gives good measure that the generator system will operate correctly over time. There is also a difference with the transfer switches allowed in NEC 517 that is not permitted in NEC 700. Emergency automatic transfer switches under Article 700 are only permitted to serve emergency loads. Article 517 allows the designer to combine up to all three branches of the essential electrical system under one automatic transfer switch if the maximum demand does not exceed 150 kVA. Here we show three example single-line diagrams, just to give you an idea. The two on the left represent possible configurations allowed for a hospital installation. The one on the right represents an installation in a non-healthcare type building. Note that when branches of the essential electrical system are combined under one ATS, the downstream distribution is still segregated into separate systems following the wiring requirements in Article 517. Both Article 517 and 700 require selective coordination. I think Dana just talked about this, but NEC 700 emergency system selective coordination requirements do not permit any period cutoff. 517.30G permits faults to occur up to 0.1 seconds. Selective coordination then applies for faults that extend beyond 0.1 seconds. In addition to selective coordination of overcurrent devices, 517.17c requires selective coordination of ground fault protection devices. When a hospital or building that contains critical care spaces or life support equipment includes ground fault protection per NEC 230.95 or 215.10, a second step of GFP is required to each downstream load. The final difference I'll mention is with multi-wire branch circuits. Article 700.19 prohibits multi-wire branch circuits from serving emergency lighting and power circuits. Article 517 contains requirements that do not allow the use of multi-wire branch circuits in general care and critical care spaces. This applies to all branch circuit wiring regardless of system, including normal power. The rationale is that disconnecting means for multi-wire branch circuits are required to simultaneously disconnect all ungrounded conductors. This could present a hazardous situation where lights or receptacles at a patient bed location are interrupted unintentionally. Okay, there we go. Here we're looking at an actual project I was involved in recently. The project involves expansion of a 130-bed acute care facility, adding 5 operating rooms and an additional 15 beds for prep and recovery. The existing facility utility service is 4,000 amps at 122.08 volts. The service transformer is rated 750 kVA, and the current peak demand in the summer months is 394 kVA based on utility bills. The original designers of the existing building included a 750 kW generator. The connected load calculations indicate 933 kVA. When we were brought on board for the expansion, the owner and contractor expressed a concern that the original design had a very tightly loaded generator and asked if they needed to replace or add a second one for the expansion. In addition to recent utility bills, we obtained the monthly test report for the generator, which indicated a peak demand of 285 kVA at 0.9 power factor. Fluctuations in demand are expected, but this was the highest demand captured in the reports. Since generators that support a hospital do not need to be sized based on the connected loads operating simultaneously, the historical demanded values can be taken into consideration. The generator is actually oversized. We anticipate the expanded area to contribute an additional 120 kVA at 0.9 power factor. The expected demand on the generator after the expansion is about 400 kVA at 0.9 power factor. This is closer to 50% of the available capacity. So the generator is still much larger than it needed to be, but with the additional expected demand, the probability of wet stacking is reduced. Now, Dana will give an overview of design load versus actual load.
Yeah, as you can see from Rob's example, what the code required those original engineers to calculate on paper can be drastically different from what the facility actually runs in real life. So I've started an internal database where we try to get our engineers to complete at the end of the project the information on the total connected design load. Then we challenge them to obtain reports back from the facility at least 12 months after the facility has been operating to obtain that real data from the utility company on what their peak demand was over that past 12-month period. So this table you see here is just a sampling from that database, but as you can see, the values can vary greatly, ranging anywhere from only 22% to 55% of the originally anticipated load. So it falls right in that range of the project that Rob was talking about at 34%. So having this data is crucial if you want to use those exceptions that Rob talked about in Article 517.30D when sizing your generators. So that's where you're permitted to use the actual demand likely to be produced on the system as opposed to the connected load demand. So this method of calculation facilitates practical sizing of generators in healthcare facilities to help eliminate operational problems associated with lightly loaded generators. So some basic tips on generator sizing is to collect real data from past facilities after at least 12 months of operation. Disregard some of those optional loads that you have connected to the system, such as chillers, when you're calculating that generator size, and you can do that on the basis that this equipment will only be connected when load is available, because it is optional. You can provide multiple transfer switches that allow you to step load the system, thereby keeping the generator size at bay. And of course, don't forget, there's always that careful balance between oversizing a generator and the need for redundancy and reliability. When you have space, multiple smaller engines tend to provide more reliability or redundancy than a single larger one. And of course, a properly sized system saves the owner money, not only in upfront costs, but also on the need for rental of monthly load banks when it comes to testing those systems that they must do on a monthly basis. So that concludes our presentation today. We hope you've gained a good understanding of all of the multiple codes and where they apply. Note that you also need to pay attention to any local requirements. Make sure you pay attention to special wiring methods permitted in a hospital and observe those installations during construction. Make sure you connect everything to the correct branch of the EES, and be sure to avoid oversizing generators. So with that, we'll turn it back over to you, Jack.
Thank you, Dana and Rob, for that first-rate presentation. And now our presenters will answer questions about the topic, and type your questions in the Ask a Question box on your screen. And please indicate which speaker you would like to answer your question by typing their name before the question. And if you're on Twitter, tweet your questions to hashtag CSE Hospital Power, and we'll get to as many questions as time allows. Additional information will be posted online at www.csemag.com, with the archived version of the webcast. And to take the Learning Unit exam, to download your AIACES Learning Unit certificate or the Health, Safety, and Welfare credit, use the Learning Unit exam tab option at the top of your screen, and the exam will open a new browser window, and you can take the exam after the webcast. However, the link will break when the webcast signs off, and the exam will be posted on the Consulting Specifying Engineer webcast at www.csemag.com with the on-demand version of the webcast. And now let's get to those questions. Dana, you get the first one. It's two parts, so here we go. What loads should be added to the emergency system over and above what's listed, and what factor should be used to account for an increase in load on the emergency systems, especially the critical, when normal power is lost for, let's say, a 1 to 6 hour time period?
All right, well, we'll start with the first one. Good questions. As one of my colleagues likes to say, codes are minimum. If it were any worse, it would be illegal. So definitely you want to, there's always times where you're going to add stuff above what I talked about on each branch. Nearly all hospitals these days are requesting cooling on emergency power, so that would include chillers, cooling towers, any of the associated pumps. That's pretty typical and pretty good thing to start including on your designs. There's specific imaging equipment, such as an MRI or an X-ray, that could potentially result in lost revenue to the hospital if those aren't on emergency. So that's another good idea of things that you should put on there. As far as the increased load to account for, it's really not that much. The bulk of what the end user has control over and changing that capacity is really just the plug loads. They're going to be moving some stuff from those white outlets to the red outlets. And your overall receptacle load in a hospital is pretty small compared to all of that other stuff that we talked about on the equipment branch, like the elevators and the air handling units and all that stuff that you're already going to have on emergency power. So really it's not a huge deal to account for. And then once you factor in the idea of what we talked about earlier, where you've got your design load versus your real life load, it's not really something that we've ever been terribly concerned about.
Well, thank you. Okay, now, Rob, you get the next question. Why are battery-powered lights required in anesthetizing locations?
Interesting question. So both the NEC and NFPA contain provisions that require at least one battery-powered light fixture in addition to any of the critical or life safety branch lighting. The reasoning for that is that even though the light should be back on within 10 seconds, it can be a pretty dangerous situation for the patient that might be sedated if there's an invasive procedure going on. If at least one of those battery-powered lights is in the room, it'll allow the hospital staff to safely terminate the procedure quickly.
Okay, thanks. And that was a nice answer to that question. And Dana, how about you for this next question? What are the recent changes to codes? And I know that you covered this, but for a refresher, what are the recent codes, changes to the codes that we should be aware of for healthcare facilities?
Yeah, we did cover on some of them. There are a couple others that we just didn't have time. So there were changes on the minimum quantity of receptacles that Rob went over. They added the change for you only have to selectively coordinate to 0.1 seconds. You've got to have those dedicated switchboard sections, which adds physical space. Another newer one that I guess I didn't mention was new is that you've got to have your life safety light and receptacles at the ATS room. That didn't used to be in there. It used to be only at the generator location. And then that AC equipment for data rooms, that's a new one. But some other things that are in there that have changed. I don't know, those of you that are familiar with NFPA 99, in 2012 they completely revamped the whole thing and required a risk assessment and said you have to do this for all hospitals. Well, in 2015 they kind of changed up a little bit. They said if you're going to design to a level 1 system, then you don't have to do the risk assessment. And a level 1 system is basically everything that we talked about here, having those 3 branches of power and everything else. Not applicable only to hospitals, but certainly affects hospitals. They added in an arc flash reduction requirement in NEC 2014, so you need to be aware of that because that affects hospitals as well as other buildings. They put in a definition of wet procedure location. Rob kind of hit on that, but in NFPA now, ORs are defined as a wet location unless a risk assessment is performed. And then something else that's kind of cool is NFPA 99 actually now allows fuel cells to be an acceptable alternate source of power in addition to that generator. Now, of course, if you know much about fuel cells, there's a whole long way to go before it can replace anything like a generator. They're expensive and they don't provide nearly as much power. But that's in there. So there you go.
Okay, it looks like we have time for one more question, and Rob, you get it. Okay, can smoke dampers or building signage be put on the critical or life safety branches?
I'd answer this one quickly.
Okay.
So, no, they can't be connected to the life safety branch. There's specific things that can be connected to that, and I don't think that either of those fall under that. In regards to connection to critical, that depends. In a hospital, if the smoke dampers are part of the smoke management system, they should be connected to the equipment branch. Otherwise, they can be connected to normal power. Building signage could also be connected to the equipment branch. There is a provision to allow connection of additional select power circuits to the critical branch deemed necessary to effective hospital operation. I have seen the critical branch used in a pinch to connect small power devices when there's no equipment branch nearby under this provision. But the intent is to minimize loads on the critical branch to reduce the chances of a fault. There may be a case to connect smoke dampers under this provision, but building signage is not really necessary for hospital operation. But if you go to a nursing home or a limited care facility, the equipment branch doesn't exist, and most of the loads permitted on the equipment branch are actually moved over to the critical branch, including the equipment required for smoke management.
So again, the engineering answer, it depends. Okay, well, thank you both. I'd like to close by thanking our great speakers, Dana Jensen and Robert Jones, Jr., for kindly sharing their time and their knowledge. And also like to extend a special thank you to our sponsors, ASCO, for supporting today's webcast.